Lesson: Data minimization and anonymization techniques. Data minimization and anonymization techniques are crucial components in ensuring data privacy and security, especially in the context of artificial intelligence. These techniques are not only fundamental for compliance with various data protection regulations, but also serve as essential tools in the ethical handling of data. Data minimization involves reducing the amount of data collected to what is strictly necessary for a specific purpose, while anonymization involves altering data so that individuals cannot be readily identified. Together, these approaches help mitigate risks associated with data breaches and misuse. One of the primary laws emphasizing data minimization is the General Data Protection Regulation, which mandates that personal data collection be limited to what is necessary for the intended purposes. This principle ensures that organizations do not hoard data, which could potentially lead to breaches. For instance, an AI company developing a recommendation system should only collect data relevant to user preferences and behaviors, avoiding unnecessary personal details. This can be achieved by employing techniques such as data aggregation, where individual data points are combined to produce summary statistics, effectively reducing the volume of data collected and stored. Practical tools like data masking can play a pivotal role in data minimization. Data masking involves creating a structurally similar but inauthentic version of the data. This technique is particularly useful during the development and testing phases of AI projects, allowing engineers to work with realistic data without exposing sensitive information. Tools such as IBM's data privacy passports enable organizations to implement data masking effectively, ensuring that only necessary data is accessible to specific users or systems. Anonymization, on the other hand, is a more intricate process aimed at safeguarding individual identities within a dataset. The GDPR defines anonymized data as data rendered anonymous in such a way that individuals are no longer identifiable. This process often involves techniques like pseudonymization, generalization, and noise addition. Pseudonymization replaces private identifiers with fake identifiers or pseudonyms, reducing the risk of identification. Generalization dilutes the precision of data, such as by replacing specific ages with age ranges, thereby decreasing identifiability. Noise addition involves introducing random data to obfuscate sensitive details without compromising the overall utility of the dataset. A practical example of anonymization can be seen in the healthcare industry, where patient data must be kept confidential. Researchers often use K-anonymity to protect patient identity. K-anonymity ensures that each individual data point is indistinguishable from at least K1 other data points within a dataset. For instance, in a dataset containing medical records, researchers can generalize attributes such as zip codes or birth dates to achieve K-anonymity, thus protecting patient privacy while still allowing valuable research to be conducted. Implementing data minimization and anonymization strategies also demands a comprehensive understanding of data flows within an organization. Data mapping is an essential step in this process, enabling organizations to visualize how data moves through their systems. By understanding data flows, companies can identify areas where data minimization can be applied and determine which anonymization techniques are most appropriate. Tools like Microsoft's Azure Data Catalog offer robust solutions for data mapping, helping organizations catalog and manage their data assets effectively. Despite the effectiveness of these techniques, challenges remain, particularly concerning the balance between data utility and privacy. Over-anonymization can render data useless for analytical purposes, while insufficient anonymization may lead to re-identification risks. To navigate these challenges, organizations can employ differential privacy, a mathematical framework that provides a quantifiable measure of privacy loss when releasing data. Differential privacy ensures that the output of data analysis remains statistically similar, regardless of whether any individual's data is included in the dataset. This approach is particularly useful in scenarios where organizations need to publish aggregate statistics without compromising individual privacy. Real-world applications of differential privacy can be observed in tech giants like Apple and Google, which use this technique to enhance user privacy while collecting insights from user data. For example, Apple employs differential privacy to gather usage statistics from iOS devices, enabling them to improve their services without directly accessing user data. Moreover, the implementation of data minimization and anonymization techniques is not just a technical challenge, but also a governance issue. Organizations need to establish clear policies and frameworks to guide the use of these techniques. The NIST Privacy Framework offers a comprehensive model that organizations can adopt to integrate privacy into their risk management strategies effectively. This framework encourages organizations to identify privacy risks, implement controls, and continuously monitor and improve their privacy practices. Training and awareness programs are also essential components of a successful data minimization and anonymization strategy. Employees at all levels should be educated on the importance of data privacy and the specific techniques employed by the organization. Regular training sessions can ensure that staff members are familiar with the latest tools and best practices, reducing the likelihood of data mishandling. In conclusion, data minimization and anonymization techniques are indispensable in safeguarding data privacy and security within AI systems. By employing practical tools and frameworks, organizations can effectively reduce data collection, mitigate privacy risks, and maintain compliance with regulations like the GDPR. Techniques such as data masking, k-anonymity, and differential privacy provide actionable solutions for real-world challenges, allowing companies to balance data utility with privacy. However, the successful implementation of these techniques requires a holistic approach involving data mapping, governance frameworks, and continuous training. By embedding these practices into their operations, organizations can not only protect individual privacy, but also build trust with their stakeholders, ultimately enhancing their AI compliance and ethics.